/swim.
He's muted himself.
Somebody's
Oh,
muted.
God. Oh, God.
What? Who's muted? Am I muted?
Yes.
You were muted.
You were muted.
No. Oh, no, I'm not. All right.
Let's try that again.
There we go, and there's the cat. Hi, everybody, and welcome to the BinPodcast. I unfortunately mute myself because I'm a jackass, but you already knew that. My name is Shartan. I am joined by Mikey, and let's see if I can get this straight this time. Wayne, and Brenna, and our special guest for the evening. Welcome, Miss Dr. Landon Noll. I'm sorry.
Good morning, good afternoon, or good evening, depending on your time zone and latitude, from your friendly astronomer who is here to talk to you about what the James Webb Space Telescope is designed to do. I hope you're all doing well, and we will be focused on what the telescope is hoping to do.
We're less than a minute in, and you've got a focus joke in.
Are
Yes.
we allowed to ask you questions about the Don't Look Up movie?
I'm not sure that the telescope was designed to deal with objects that close to Earth. In fact, it's actually designed to keep away from Earth, because Earth and the Moon are big glowy balls that are quite obnoxious if you're trying to observe in the place that the telescope is designed to observe. So answer is no. It can't see things about looking up. There are other telescopes designed to do that, but James Webb is not one of those.
Okay. So let's just get into the weeds then. What is the telescope designed to do?
Well, the James Webb Telescope is designed to observe primarily in what we call the infrared. You're familiar with the rainbow, colors of the rainbow, right? And in that colors of the rainbow, the James Webb can only see the orange and red visible part of the spectrum, but it goes way down into the infrared weeds. So if we think about in terms of wavelengths of light, and I'll use it in micrometers, goes, normally you can see from about 0.3 to about 0.7, maybe 0.75. That's your visual range, right? Between 0.3 and about 0.75. James Webb goes from 0.6, so that's just the orange red part, down to 28.3. So it actually, your visual spectrum is one octave. You think about it in terms of frequencies, one octave. And James Webb goes down several octaves below. So it actually could see several rainbows, but way down in infrared. And there's a very good reason for that. The things that it's hoping to study are primarily glow down in that longer wavelength than what you can see. And there are a couple of good reasons for that. Some of the objects it's designed to see are very far away. In our expanding universe, they might be stars that are glowing in visible red because they've been redshifted. They're so far away, they've been redshifted. They've been redshifted way down into wavelengths that are too long for you to visibly see. Other things it's designed to see are objects that are not as hot as stars, like planets or planetary systems in a process of accreting to form, right? Things that are cooler than a surface of a star. And so those things that are particularly in infrared are what it's designed to see. The reason why it wasn't built on the ground is our atmosphere interferes with that stuff. The atmosphere is actually quite opaque to a number of those wavelengths in that span. From the 28.3 up to 0.6, there's spots where the atmosphere just looks like a fog. Other things are like water vapor glows in those things. So you actually have emitters, and even the Earth itself has a temperature and it glows. So one of the things they couldn't put it on the ground, even on a high mountain, because the glow of Earth would just swamp those detectors. And in the atmosphere, even very thin water vapor stuff and dust has a temperature and glows. It couldn't be near Earth, orbiting Earth, for a couple of reasons. One is that the telescope itself would be its own source of brilliance. So imagine you build a telescope and you stick light bulbs all around the telescope, right? To see the telescope. Well, yeah, that kind of defeats what you want to look at. The same thing, the telescope itself has to be cold, otherwise its heat would overwhelm it. It would see its heat and just would see this big fog of glowy spectrum. So the telescope itself is designed to be very cold, operate what we call 50 Kelvin. That's minus 223 Celsius, or for those metric, they challenge minus 370 Fahrenheit. It's meant to be very cold. So at those temperatures, it's not glowing very much, and enough that it can see very faint objects, and it's not going to see itself. That's one of the reasons why it's also parked at a place called L2, which is very far from Earth, about 1.5 million kilometers, or about, I guess, around 900,000 miles away from Earth at this point. So that even the Earth and the Moon, even the light and heat of the Moon would overwhelm this telescope. So one of the things that it also, of course, the sun would completely blind it. So the James Webb Telescope has a field of view about 40% of the sky looking away from the sun, right? So anything that is 40 degrees from, if you think about the sun, Earth, Moon, it's behind it's sort of in line with the sun, Earth, Moon, behind that, and it sees out there about 40% of the sky. And what it means is if you want to look over there, you have to wait 6 months or so for you to be on the other side of the sun to look at that. So at any one time of the year, it can see 40% of the sky. And so people plan on saying, if you want to see over there, wait a couple of months until it becomes in prime view and then look at it. Again, because the sun is, of course, really hot, and it would swamp the very sensitive detectors. This is meant to look at very faint things that are either cool compared to the surface of the star, or so far away that the star has redshifted down into those wavelengths we can't see.
What kind of
yes, go ahead.
What kind of detectors are on this satellite? Like I know there's several different kinds, like X-ray and gamma ray and all that stuff. What is there a specific name for the type that they use? Because I saw like the big crazy mirrors and all that stuff. So like the bare bones of it, like mechanically, like how is it working?
It has several detectors, and the detectors fall into two general classes. One is just an array of cells that you might have in a camera, basically a camera grid, to detect light over an area, and the other are it's called spectrograph, to break light into a prism and see the individual frequency components. This telescope is an analysis telescope. It's not a survey telescope. By that meaning, you wouldn't use this telescope to go and hunt for things. You would look for known things to analyze what it is. And here's why. The widest field of view of this telescope, this is a very narrow view. The widest field of the telescope is what we call 2.2 arc minutes. Now, think about the full moon. It's around 30 arc minutes. This is about 1/15 the diameter of a full moon. So it would, if it was looking at the moon, which it can't because the moon's too hot and glowy and it's too close towards the sun. But the moon would take 15 pictures just to go across the surface of the moon. Another way to put it in terms of its field of view, imagine you see headlights of an automobile. It would be able to, if that automobile in its widest field of view, if you had an auto that was at a distance of 3.125 kilometers away from you, so I guess miles, around what, about 2 miles, something like that away, it would the two headlights of that car would be on opposite parts of the field of view.
Oh, wow.
So very, very narrow, right? It's very, very narrow thing. It's not a giant wide field telescope stuff. It's a very narrow thing. So when you want to look at something, you need to know where you're looking and pointing at it, and then it'll stay there. So it won't, like the Hubble, give these giant panorama stuff. It can, but it's go picture. It'll take a while to build up a larger area. And you need that kind of resolution because some of the targets for this thing will be, hopefully we'll be able to see some of the first stars that formed after the Big Bang. We'll see some of the first galaxies that formed after the Big Bang. There's a big question about kind of a chicken and egg thing of which came first, the stars or the galaxies, right? And probably the answer is a combination of both. But did galaxies form from the first stars switching on, going supernova, compressing gas to form a large lump, or did large lumps come together for which stars started to form? Did the galaxy lead the star formation, or did stars lead the galaxies? And what are the nature of those first objects look like? So that's that case where those objects are what we call they're redshifted to a factor of 20, meaning that they're so far away that light has been stretched. Their light frequency has been stretched out 20 times. So they might have been nice and visible in the optical spectrum, but they've been shifted way down because the universe has expanded so much. They're so far away, receding so far away, for all to us, that they've been shifted way down to 20. So we think that the telescope will be able to look at the earliest stars that formed somewhere around 100 to 200 million years after the Big Bang. After the Big Bang flash, that thing you might have heard of, the cosmic microwave background radiation stuff there. Well, after that flash, when the universe went from transparent, translucent and transparent, right, and the photons just took off, longer because all most of the atoms combined into neutral stuff, that you had what we call the dark age, where there was really nothing emitting light. There was no stars, right? You just had a bunch of neutral gas, and it took, we think, somewhere between 100 to 200 million years before lumps came together enough that stars switched on. And so one of the things this telescope is hoping to do is to see those first stars and to get an idea about what their nature was like, as well as to see galaxies come together. Well, that's the far red stuff. Go ahead.
I'm just a bit in awe of your description of how the telescope works. When you mentioned octaves and spectrums of light, that I could straight away visualize. I'm going to nick that and I'm going to use that in my description when talking about this. I'm taking it as my own, but because I
think you're a musician, or you're just familiar with music.
Well, I'm familiar with. I wouldn't call myself a musician. I'm familiar with music. I can play a guitar, but
no one does.
To say that the octave of light that we can see is this, and then you visualize someone down tuning the guitar to a point where the vibration is so low that you can't actually hear it, or so high that you can't actually hear it. That is a perfect illustration of our very limited field of view when it comes to light, and I thought that was really, really good.
Well, thank you. And if you think about going take that if you're familiar with your a modern 88 note piano, okay. What the telescope is that the optical part of the telescope would be probably the highest 3 or 4 notes on a piano, and it has a full range of another 6 octaves below what we can see. where the universe portrays this rich tapestry of frequencies, of sounds. And we've come to know that certain chemicals out there, certain objects have glow, have patterns, have harmonics that tell you a lot about the nature of what it is. So it's not simply just saying, oh, there's a star, but what type of star? What's in the star? What's around the star? Or the galaxy? What type of a galaxy is it? Is it just a bunch of point sources? Is the galaxy all glowing? What is the nature of material? So if you want to know the chemicals involved or the elements involved, you need to see the spectrum. You need to hear the harmonics of the sets, which are there all the time. It's just that down here on Earth, we are surrounded by this cacophony of stuff. Even just the glow of the Earth, even going to a place like Antarctica, it still has a temperature which causes the glow completely swamps the set. Plus the water vapor just saturates.
So what you're saying, it's been positioned in a way so it's in an area where it's effectively a blank canvas. There's no interference. It can look at what it's designed to look at without any of this background stuff coming in and disrupting the readings.
Yes, and so it has been put into the effectively of a sound studio without the coughing of the audience, without the noise of the traffic around it, where it can concentrate just on the music of that.
Yeah, it's basically a noise gate apparatus, right?
Yes, yes, and in that sense, it had to have a very unique thing. The traditional way we've done telescopes that because we've observed in the infrared before, but with limited telescopes, so things like the Spitzer telescope, that had a vat of liquid helium cooling its cameras, and the way it cools the cameras is you let the helium evaporate, right? When something evaporates, it takes heat from its surface and radiates out in space. So that's how a typical dwarf flask system works, and that's fine. The problem is that when you run out of coolant, the thing warms up.
Can you talk to us a bit about the solar sails and the deployment of them and what purpose they serve?
And so that's actually why I'm talking about this. It's exactly about this sort of thing. That they could have put a giant tank of liquid helium on the telescope and let it evaporate slowly. There's a couple of problems with that. One is you get helium gas around the telescope, which has kind of interferes with stuff, with things. Particularly if you're trying to observe helium, one of the common elements there, it gets involved in it. The other thing is that it limits the lifetime of the telescope. So that instead of it being actively cooled by a cryogenic flask of liquid cold stuff, which would also add the weight and complexes things, it passively cools itself. So it has this giant sunshade, even though it's kind of behind the Sun Earth system. It has this sort of sun shielding, which has an SPF of around 1 billion, if you talk about it in terms of sunscreen capabilities, right? Where the things about the size that has basically this giant umbrella shade that's about the size of a tennis court, and and the telescope sits behind that, and that allows it to cool itself passively, right? So there's no liquid stuff that boils away, and once you're done, you there. It actually works. So we look right now. The hot side, the side that's facing the sun, is around 54 Celsius. And that, I guess, in Fahrenheit is around 130 Fahrenheit, right? It's facing the sun. So it gets a glow from the sun, because even though it's a million and a half kilometers away from Earth, it still sees the sun, right? It's pretty much has sun brightness of things. The cold side is around 211 Celsius right now, which in Fahrenheit's around 3 minus 348. So it goes from 150 Fahrenheit to minus 348 Fahrenheit, from the front side of the shade to the back side of the shade. And that's really critical. Now you might say, well, why don't you just park it straight in line where the Earth shields it? And the answer is it also has to have solar panels. Right? This thing needs power. And so you could put on a giant reactor there, but that's going to be glowy, warm, and messy and so forth. So it needs solar panels to power itself. It takes about 2 kilowatts to run the telescope. So on the sun side of the shade are solar panels to collect solar power, which is one of the reasons why it has that odd orbit. It's orbiting around in L2, but it's not right in line. It actually has to be a little bit to the side and kind of orbit around it, so that the solar panels can still see the sun, but the telescope points backwards, so that with this giant sunshade, again, because you want the telescope to be cold, you don't want the glow of the telescope to blind itself.
But again, forgive my ignorance. I'm not that well versed in this, but I was under the impression that with like a solar sail such as that it has, that the photonic light from the sun would repel the telescope and give it some form of propulsion.
Yeah, I mean it does. Yes, and it does have a good push on that. But the one of the things that the telescope does have are little thrusters to keep it within that orbit. And in fact, that's probably the limiting factor on the length of the mission of the telescope. The telescope has a nominal period where it is the initial design of the telescope is to operate for 5 years, right? That's the current planned phase of it. And they think that they can operate at least 10 years. And what's wears out? Well, the thruster is necessary to keep it in that orbit, to keep and to do the sort of the orbital motion of it, to control exactly what you do. That's one of the things that can control. And so its limiting factor right now is that propulsion, to do that fine adjustment to keep it parked in this orbit around something called Lagrange point 2. The telescope, in theory, could be serviced, but it's too far away for people to go into this. It's way farther away than even geosynchronous satellites. It's way out there, and so it would be impractical for people to go and service it. It'd be much harder than let's say going to the moon even. And so instead, it's possible that a robot could come to the telescope. It's got markings and a portal there. A robot could come to the telescope and refuel it. That's theoretically possible, but not planned. I have a feeling if the telescope is doing great things, and it's nearing the end of its fuel life, there might be a push to design a robot to go out and do so. And the argument would be that these kind of refueling missions would be useful for doing, space exploration. This is a good practice, and we get a lifetime. The telescope, but the telescope itself has you'll see has a nominal plan where they say, okay, we're designed to allow this design at least 5 years. Now, the reason why it was 5 to 10 was because some of that fuel that it has might have been needed to adjust its orbit, right? Had the launch been not as perfect as it was really picture perfect launch, and launch windows, it would have needed more fuel to course correct itself. And that fuel it uses to course correct would have been the stuff you would use to extend its mission. But because they did such a successful launch and getting to where it's needed with very, very, very little course correction, it's got a lot of fuel on board, and it basically doubled its lifespan.
Well, I mean,
Now-
if somebody needs to go out there with the jerry can and fill it up, if they need me to take like a weekend off,
Yeah.
I don't mind. I can go
Yeah.
up there.
But it's right now, the motion right now. So the biggest fuel load it took was to slow down, right? There is this notion of coasting out there for almost a month, but you needed to put his retrorockets on to slow down to come and to park it, right? And so entrance into the thing, and now its motion now are only around 200 meters a second.
Is it still within the Earth's orbit and not being interfered with by the moon?
Okay, so yeah, it's out at L2, and again, that's the spot. That's kind of the sun, Earth, moon. It's behind, out farther away. It's behind. L1 would be on the front
Interior.
side, the sun side. Yeah,
Right,
there's the exterior one there, but it can't be exactly there because the Earth's shadow would cast it and cut off light from its solar cells. So it has to orbit around that point, near that point, and spend its time to get stuff. But it has this giant sunshade with an SPF 1 billion to block the light, so that you drop the temperature from 54 Celsius down to minus 211. And right now, the current mode it's in right now is to do the fine adjustments. First of all, they want to drop the telescope down even farther, right? The current temperature is still got to cool down another I think around 12 degrees Celsius. But that's just from the leftover latent temperature from being on Earth. So it's got to drop down even further. And during this period of time, they're going to be doing fine adjustments on those hexagonal mirrors. Have little actuators to move it, nanometers to get that stuff. So they'll getting the focus really well. They learn from the Hubble. Don't assume the manufacturer is going to manufacture everything perfectly, and so they retested. Plus, they have enough adjustments that to correct any things that need to be corrected. So during this period of time for the next 5 months, they're going to be refining the system, letting it cool down, as well as understanding the characteristics of the camera, right? If there's a stuck pixel someplace on one of their sensors, they'll be able to note that, so that when observers come to observe, astronomers come to use the telescope, they know if you see a spot there, that's what that bad pixel, right? We don't know. I don't know if the cameras are perfect or not. Most likely they're not. There might be some parts of the camera that are more sensitive than others. So they will take known fields and kind of get a sense for the color balance and the brightness balance to be able to let a researcher take the data and understand how well is it actually working, and if it's got certain oversensitivity of certain frequencies to others, they'll be able to calibrate that thing. So it's a calibration mode. There'll be a couple of pictures that'll come out with this is typically what NASA does, because senators who funded this thing want to see something, right? They want to see, so they'll put out some publicity photos for that purpose.
What if they turn it around and point it at the Earth and we actually see that it's flat?
Well, that would of course would do a couple of bad things. It would start to heat up the telescope. It would also blind the telescope. The sun's blindness, even the Earth, right? The Earth.
We'll never know. We'll never know.
Yeah.
That's the whole point. It's a conspiracy.
So you can't look anywhere near, and the moon is too bright and too hot to even see the moon. So when you talk about that line of sun Earth, it's the 40 degrees. It's a 40% of the back facing motion. Anything to the side,
So that's its field of vision.
It's basically, think about if you've got if you have if you talk about it has a it's not its field of vision, it's its ability to point, right? It has
Right, okay.
it has you know, of the 100 degrees that it can look at, at 100, it can point anywhere within 144 degrees back from the Earth Sun sign. So you think about, again, if the sun's behind you on the Earth, the telescope can look essentially at 4 degrees of the 40% of the sky.
Okay.
If it was 50%, it would be able to see side to side. But it's 40%. But problem is when you start to see side, now the glowy sun back there starts to come into the telescope.
Mhm.
So it's kind of like got blinkers on.
And so
all that light goes that way, and you can just see in that vision.
But remember, we're talking about where it can point.
Hmm.
Its actual field of view in its widest camera is only 2.2 arc minutes. That's seeing the headlights of a car at 3 kilometers would be that. It's 1/15 the diameter of a full moon. So it's a very, very narrow telescope. So its field of view is actually extremely small. That's because it's designed to study something that we know is there, as opposed to get the big picture. This is an analysis telescope. Now, I should mention, by the way, because I'm a planetary astronomer and my planetary astronomer friends are screen saying, but tell us about the other part of the mission, right? I've talked about observing the first stars and the star formations of the first stars after the Big Bang and the first galaxies after the Big Bang. Another very important constituent are planets. There are things that are much colder than stars, and so it's designed to look at planets, atmospheres of planets, and stuff. And for example, this telescope will be capable of trying to study the gases of a planet around a nearby star. Not just the planets in our solar system, the planets out there that have where you hear about saying, well, they think they discovered some rocky planet that's in the Goldilocks zone where it's not frozen, it's not boiling, it's somewhere in the middle. That's nice, but given our current telescopes, we don't have the ability to analyze what's in its atmosphere. Because the next thing you want to see, if you're looking for possibility of life, is you want to see, does the atmosphere have complex molecules, whatever they may be it traditional Earth organic or some other crazy chemistry, right? Presumption is if you're seeing life, you will see complex chemistry going on. Those chemical things have their resonance. They have their little tone that they resonate in. And those frequencies are on the cold stuff. It's not surface of a star temperature. It's much colder. So again, you need that infrared. You need to see the resonance modes of the things. Again, if you use the musical analogy, it's you want to know what is the blend of frequencies. So a violin sounds different than an oboe because the overtones, the harmonics of a violin are different than an oboe because it has a different mechanical structure. The same thing, different chemicals with their appendages and long chain stuff have different resonance modes. So if you know about a star having a planet orbiting it, when that planet is to the side, the telescope will be able to look at that planet and begin to analyze the gases that are in that planet. There's also a thing called a star-shaped system where the really extreme cases, we find a planet that seems to have rich in stuff, is they'll have these little star shade missions. It'll be this umbrella, that has a big giant shade, think like a giant umbrella that will be it may be as a couple meters wide, a couple yards wide, and that umbrella will fly in an orbit maybe couple million kilometers away from the telescope and just come right in front of the star. So they'll time it so that they know the orbit of the planet, and when the planet's to the side, this shade will come in front of the star, block the light of the star, and the very sensitive telescopes of the camera will go out full wide stuff and stare at the planet to not only image the planet but be able to do chemical analysis of what's in the atmosphere of a planet around another star. That's how sensitive this thing is, and that's where you're going to go from here's a planet that's rocky, that's got an atmosphere and is not too hot, not too cold, to here's a planet, it has some oxygen, it has some carbon, it's got some nitrogen, it's got some rich chemical blah, blah, blah things in it. That's where we're going to start to see foreign planets with a rich environment, or solar systems that are in the process of forming, right? And stuff where it's a cloud disk around an early star that's beginning to lump into planets and see the process of planet formation. All that stuff happens at lower temperatures than stars, so its frequencies are much lower than stars. So again, the three principal things are analyzing the first stars and the first galaxies redshifted way out to like 30 times their length, or things that are not glowing star surface, which are planets, asteroids, things in the process of forming, and things that are formed, to do real analysis. And that's why it's very, very narrow, right? You don't want to have a wide field where you're getting all kinds of star glow. You can zoom in on a planet next to a nearby star that's glowing only at a couple hundred degrees or less, and not be blinded by the glow of the Earth, not even blinded by the glow of the telescope itself because it's cold, it's behind that sunshade, and be able to analyze the light. So it's an analysis of that thing. And we're going to learn some really surprising things about which came first, the chicken or the egg, the galaxy or the cat.
So is there any schedule right now? Because I know you were saying that they have to drop the temperature of the telescope more to get the best imaging possible. But how long do we have to wait? Is it going to take a month for them to cool this thing off? I don't want to, because Landon, let me tell you something. I don't want to wait a month.
You've been waiting.
I've been waiting for years for them to launch this thing. They launched it on Christmas. It was a great launch. Cool. Now you're going to make me wait even longer after you done park the car? It's like when you get to you're stuck in traffic, you get to the mall, you finally find a parking spot, and now you can't get out of the car because mom has to finish listening to "We Wish You a Merry Christmas" for the last time, so you're stuck in there for another 4 minutes.
And it's like, it's worse than that. You just got off the airplane and you're waiting for your luggage.
Oh,
Landon, before you answer that, I just want to circle back to the musical analogy. So what you're saying is this telescope is that sensitive that it can look at planets all playing the same chord, but when it looks and analyzes them properly, it can see the tone, so you can differentiate between the different instruments, i.e. being the different gases that it's formed.
Exactly. And the resonance, the resonance, you'll see a bunch of spectral. That's why it's called a spectrum, right? It's going to break it up into its musical notes of almost 7 octaves, but much finer than a note. I mean, it's not just half steps. I mean, it's really fine microtones. And the harmonics of a gas doing some chemical dance thing are going to show up, even though you might have the same temperatures, the same principal peak. It's
that's what I mean.
Overtones that are going to tell you that's an oboe, not a violin.
Yes.
Right.
Yeah. That's
the structure of the thing.
Dare I intrude? But according to your analogy, they'd be able to tell you what kind of strings are on the guitar.
Yes.
Yeah.
Yes.
Yeah.
And how well the guitar was tuned, whether the tech knew their thing, or it's like a harpsichord, which is a wooden structure which goes out of tune rapidly. So back to your question. It's expected to spend about 3 to 5 months.
Whoa, poor Mikey.
Calibrating.
Mikey, when's your birthday?
Oh, Mikey.
Sorry. So you I know
Today's first rage quit.
I know you're the passenger.
Hang on. There was a rage quit and it wasn't your time. What's going on?
as soon as they opened the cabin door, Mikey was out that door even before they say, please, blah, blah, blah. You're out there. But guess what, Mikey? It's going to be 3 to 5 months before your luggage shows up down there. So chill, cool down. Now I have to say, the
Bullshit.
I won't talk about too much of the history of the building, but I'll tell you that the folks I've talked to with the regards of the construction were saying all these years of delay was fortunate, because had they launched the thing when it was first built, it wouldn't have worked. Right? They discovered a number of things, and so part of it was learning from the mistakes of the Hubble and saying we only got one chance. Right? This was not something that another shuttle launch could go in and fix things. This is it had to work or it doesn't. Right? And it's extraordinary skill as well as care went in to get to the point where there were many spots, hundreds of spots where had something gone wrong, end of telescope being useless, right? And so it managed to survive because they did a testing and really they discovered a number of things. Had they launched that way, the telescope would have been a total waste. So the delay that it took was uncomfortable, in part because we want to have this window of time where the Hubble is still working and the James Webb is working, because there's some object where you want to get both perspectives. So when you're talking about the 3 to 5 months is where they're going to be testing, calibrating, as well as cooling the telescope even more. And then they've allocated time. So right now,
you just broke my heart. You literally just broke my heart. I was thinking like in the next week or so. I am so sad now.
So understand that there'll be a couple of images showing up, because as they begin to do these testing stuff, there's a couple of targets and they'll basically show what the telescope is doing, right? But also they have to characterize things. But when you set up a sound system, how many times have you set up this perfect sound system for your podcast and someone's muted?
I can think of one time today.
So part of the thing is to get the software, get the calibration, characterize how sensitive mic is over those frequencies.
I'm very sensitive.
Yeah,
I feel attacked.
Obviously.
I feel attacked.
Why do you feel attacked, Chartan? Explain.
We're using a new system, and they did it wrong.
Okay. I didn't. I'm the most technologically inept person here.
Landon, I don't know that I can have you on the show anymore, because you have literally, I was so excited to have you on. I was so excited. I was thinking, maybe they'll have images up today. Maybe Landon's got some secret pictures from his space friends that he's going to show me. And you're telling me it'll be summer.
Yes. So for now, understand that 3 to 5 months is for when it becomes full science, right? It's going to go from calibration and testing, fine focus, cooling, to full science in somewhere between 3 to 5 months was the plan.
Can I pay them extra money for them to do it faster?
And so there'll be some images produced. There'll be some that when you get to the point of they've done the focusing and some test images, right? There'll be some. So during that time, you'll get some sort of images showing again.
Trailer.
Yeah, but understand we won't be able to show you what the telescope sees.
It'll be at the Super Bowl.
You can't see it. You can't see those. So there'll be these false color images that have got that your monitor only gives you 1 octave of frequencies, and this has got almost 7 octaves of frequencies. So you're going to have to compress it in order to see it visually. Now for someone is doing a spectrometry where you see the rainbow, the patterns, lights. Though that's the music of their ears for understanding analysis of. But for the pictures, you've got to take that almost 7 octaves, compress it into 1, and you've got to basically scale it up to visible to see. So those images will be false color images, and But I think they'll be impressive, and you'll see some of those come out as they're doing these assessing. So you won't have to wait that long to see an image from the telescope. But if you're an astronomer waiting to do a research program, you want the telescope to be working, and you want to understand the sensitivity and how well, if there's stuck pixels or there's pixels that are slightly sensitive because of something happening. You want to know that so that when you get data, you understand what it's telling you. So right now, they took this happened a couple of years ago where they took proposals saying for the first year, what do you want to do? And so they awarded 460 hours of observing time to 13 programs to look at our solar system. So places, things like Neptune and Pluto and things like that. Exoplanets, planets around other nearby stars. Stars and star formation, putting the ones way far away, some of the first stars. Galaxies, gravitational lensing of stuff where the space is warped around a heavy object and you can see some gravitational lensing of things. And quasars, the surrounding of a black hole that the surrounding gas is radiating stuff. So they'll be able to see, again, narrow field of view, very high magnification, very sensitive, so known objects. And so they have a bunch of proposals there. They put out a general proposal and where they had 1,173 programs of people submitted saying, here's what we do with a telescope. That would have made 24,500 hours, but there's not enough time in that first window. They only have 6,000 hours. They only have 6,000 hours in that first up to the first year, excluding the calibration stuff. So they had to pick of the 1,173 proposals. They picked 226. Of which 13 are these large-scale proposals that do a whole bunch of stuff, right? Someone looking at asteroids near Neptune or comets or things like that. But they also are reserving time for something comes up, right? A star explodes, a new interesting exoplanet discovered, right? A comet is discovered. That's going to be an exciting thing to have this telescope look at comets, look at the tail of a comet, look at the comet, to understand the chemistries involving on the surface of the comet, right? And so they have not allocated the full 7,600 hours. They've had programs for 6,000 hours with the notion if something major comes up, someone's schedule has to be bumped there, but they have enough. They also have to have time for doing calibration and stuff, like when they reposition the telescope because the sunlight has pushed it away or something like that. They'll have to settling down time, so there'll be maintenance time. There has been this allocated time. There's some time reserved for if something comes up, and exceptional things happening.
So we have another astronomer on the streamline, and we didn't tell you this. She's being very polite and very shy. But didn't you do a little spaceography in college there?
I did. I studied astrophysics at Santa Cruz.
Oh, excellent.
So actually, I have a lot of friends who are still studying. Some went to Caltech and places like that. Yeah. But I want to know. Well, I mean, I know, but the world will probably want to know.
Calm down, Brenner deGrasse Tyson.
Why we name things very specifically when it comes to space. Why was this particular infrared telescope named after James Webb?
James Webb was an administrator of NASA between, I believe, 61 and 68, and he was the one who basically oversaw the Apollo program. So between Kennedy's push to we're going to go to the moon to the the Apollo 11 launch and so forth and so forth, he was the prime administrator for getting NASA ready to go to the moon. And so that's where it's honored for his leadership in there. And that was really the kind of the formative stages of NASA. He played a role, and that's why it is so honored. This telescope is that major that someone that significant in NASA was honored in that respect.
So what we're saying is James Webb is the reason why we continue to have space programs, studying it, putting people into space, creating better technologies, because James Webb was the one that said, like, we have to go to the moon. We have to do this.
Well, you might say that President John F. Kennedy said we're going to go to the moon, but the question became how, right? And so the head of NASA was the one who got the order from the president to then come back and say, here's some of the costs, here's how many people, and particularly in there was a lot of early disagreements on how to go to the moon and technology is necessary, right? And so the development of computers, the development of ceramics, the development of guidance systems, the notion of would the telescope, would the Apollo program be purely robotic with people involved, or mechanical, or purely mechanical? A lot of those critical decisions, as well as like when he had Apollo 1 fire, how to bounce back from those things. So he played an important role in the leadership there. I should also, by the way, mention you just casually dropped UC Santa Cruz. Folks, UC Santa Cruz is a very important part. Plays a very important part in astronomy, right? It is one of the few universities that has a separate astronomy program. It's not just a sub-department of physics. It has a real astronomy program, and even
is very influential in observing.
And so one of the things as well is for example the Lick Observatory. That was funded by James Lick and did a lot of foundational work in astronomy, is actually managed and administered by Santa Cruz as part of the program set up by James Lick. James Lick wanted to build a scale replica of the Pyramid of Cheops in San Francisco, would be in the financial district. He wanted to build for himself a scale replica so that would be his tomb, right? And we would have had this giant pyramid there. But a couple of administrators of the early University of California came to Lick and said, pyramids that's been done. You want to do something better. You want to be known for the greatest telescope. And in fact, you want to be buried in the pier of the greatest telescope. In fact, today, if you go up to the Lick and you see the great 36-inch refractor, the largest refracting operating telescope in the world, you go down there, you'll see the thing. Here lies by the body of James Lick, looking up in the pier. Obviously, it's entombed. And so that's all administered by UC Santa Cruz, right? Now, and even much to my good colleagues at Cal, they kind of Berkeley sort of says Cal. We get all of Cal, right? But they call themselves Cal or UC Berkeley. Do heavy use of the Lick Observatory administered by Santa Cruz. And one of the things that's key about Lick is that it's a world-class observatory for which undergraduate can actually get time. So if you, for example, are a student working under the tutelage of like great astronomers like Alex Filipinko, you can actually use telescopes up at Lick to do things. And in fact, stuff like, for example, learning the universe was accelerating. The ability to detect what we now call dark energy came from key calibration came from a telescope on Lick, administered by UC Santa Cruz and run by astronomers at both Berkeley and UC Santa Cruz. So I know you don't want to push your alma mater there, but I wanted to recognize the importance of the world of astronomy and the many telescopes that Santa Cruz is involved with in their, not just at Lick. They've got stuff at Mauna Kea, stuff in the Canary Islands and so forth. So it's a great astronomy program. So I wanted to honor it.
Landon, as we have you here, and you're a great orator on all these subjects, just to have a little bit of fun, just to shift gears. I would like you to dispel all of the conspiracy theories about the moon landings, because there's too many out there. We have you here right now, and we at the BIM podcast can shut them all down right now.
Okay, so a couple of things, right? Let's keep on the Lick Observatory theme. The observatory administered by Berkeley and often run under a program from Cal Berkeley. I used the 3-meter Shane telescope and a 60 kilowatt laser pointed at the moon and bounced off of the mirrors from Apollo 11 and Apollo 14 and timed the set. So it took about 1.25 seconds for the light pulse to go up to the moon, and 1.25 seconds come back, and I helped do the refinement of the distance between the mirror of Lick and the mirror on the moon left by the Apollo astronauts to a distance of about 1 millimeter. We were able to measure that, and that was necessary because there was kind of slop involved in a couple of centimeters for things to refine that set, and that was good enough that over several separate pulses, we were able to prove continental drift. We were able to see the motion stuff. Now, it turned out the big error was that the Earth is a wobbly, wiggly thing. So the moon has tides on it that stretches the rock, not just the ocean, but the rock. And there's earthquakes and so forth. So I had part of a precision clock, one of the precision clocks, to try to figure out where Lick was and all those things. But all that stuff is a program to do that. And that would not have been possible if it were not the fact that the Apollo astronauts left mirrors on the moon.
But what about the Van Allen belts? We got you there.
And that radiation is opaque to the green laser thing that the pulse went through up and back. And so you need to think the way that thing worked was, you turned off the camera and you flashed through the optical system this 60 kilowatt pulse, right? And it was typically around 20th of a second, a very fast pulse. And once the laser was off and on glowing, then you turned on the camera and you waited the roughly 2.5 seconds of the round trip. And then you saw the blink, because lasers do diverge, and by the time it hit the moon, it was several kilometers wide, where you have this object is more like the size of a large TV monitor that retroreflected the thing back with corner reflectors, and you needed 3 meters in order to get the blip there, to see the blip come back from the moon and the timing of it. And so that was one of the things for their stuff. Second item would be that I am a frequent visitor to the South Pole. In fact, I had a nice conversation with Steve McRae where I was standing on the South Pole. Right? And when I go there, we're looking for, again, I'm a planetary scientist, and we were looking for basically we're scanning for meteorites, rock from outer space that are embedded in the ice. And around, south of 80 degrees south, and since we're in the area, I take people to the actual South Pole, and then go through the process of locating to the point where it's about the size. We know the area with the size of like a sugar cube, or your thumbs. You can put your thumb saying the South Pole is right here, right? It's not like the North Pole, where on the North Pole you're on an ice pack on an ocean as current there. Yeah. You can never say, we went through the South Pole there. With the South Pole, because it's frozen, you can say it's right here, right? And
can I ask, why would you go to the South Pole for more frequency of that? Is there more, for want of a layman's term, is there more gravity there, or are they?
I think it's actually less. There's actually the thing that is there is that there's well, first of all, it's a high altitude. The air is very dry there. So if you can't be a James Webb telescope, the next best thing is to go to a desert, and Antarctica is a desert. The snowfall is measured, annual snowfall is measured in millimeters a year, right? It's like a couple of dimes, stack of dimes worth of snow in a year. So it's very, very dry there, high altitude. You're under the ozone hole, so you got to also have lots of ultraviolet stuff as well as there's not many radio transmitters. It's very, very quiet optically there. And it also has there's a South Pole telescope and group there of instruments at the South Pole vicinity is doing some amazing work. Hopefully there's something called BICEP 3, which is gathering data regarding the last time that photons before the Big Bang flash, their last reflection off of the plasma before the plasma went transparent. The polarization is going to hopefully allow us to have a really definitive check, maybe, assuming the data shows up, on the gravitational waves that occurred, the sonic waves. Remember, again, the sound, right? The early universe had these literally these sound waves of pulses going through the universe that have been stretched way far now that in our today's thing. So the at the time of the Big Bang flash, 378,000 years after the Big Bang, those pulses, those sound waves were around 550,000 kilometer, 550,000 light years across. They've been shifted now to around 500 million kilometers, 500 million light years. So they've gone from around half a million light years to 500 million light years. So they've stretched over 1,000 since that time. And one of the things you want to look at again is the harmonics. Now the resonant frequency of the universe right now has been redshifted at front time almost 1,100 times more. So back to musical note analogy, the fundamental tone of the universe right now, the Om, if you will, of the universe, is 71 octaves below B flat.
I can sing that.
Go on then. Do it.
I'm doing it right now.
It's a way down there, but you're not only interested in the fundamental tones, but all the overtones, because the overtones give you a notion of what kind of musical instrument you're talking about. And again, the sound waves of the universe is something that there's a telescope called BICEP 3 are studying, because fortunately it's looking at wavelengths much longer than what the James Webb can see, that at least you can see at the South Pole. So those are other things there. And I guess the final thing I should mention, so if going to the South Pole is bad enough, or the North and South Pole both, was the recent eruption in Tonga, where we have an Earth observation section. I'm now up in the very far Pacific Northwest corner, right up next to Canada. And we have a sensitive weather instrument that detected the atmospheric pulse from the blast that occurred at Hunga Tonga, and it traveled. So we saw the pulse traveling directly from Tonga. We also saw the pulse that goes around the world to the other side, and we saw the second pulse come back through. So it was a blast so powerful that it went around the world, shockwave heard around the world, and we saw the forward motion and then later on the backward motion. And you can calculate the average temperature and the mean path and so forth. It was a really beautiful set of stuff to which is possible on a spherical Earth, or spheroid Earth, I should say.
So can we use the James Webb telescope?
Okay, no.
Go ahead.
No, go for it. I thought we were done with the James Webb. We started talking about conspiracy theories, and now I had a third question, because we had a very interesting weather phenomenon in Norway and Sweden.
Sunshine?
Phenomenon.
Sunlight?
No. So during. But if you want to go back to James Webb, and then I'll ask my question.
So back, I say that the summary of the thing is James Webb Telescope. It's impressed that it worked. Right, it had many points of failure. It was delayed, but we were fortunate that the delays basically caught issues so that it was able to work. It's now in its parked orbit, where the solar panels can see the sun, but it's got this giant light shade so that it can cool down several hundred degrees from the hot side to the cold side, so the telescope doesn't blind itself. It is got a ability to see 40% of the sky facing back from the sun, and if you want to see the other side, you just wait until the orbit of the Earth goes around the other part of the other direction. It is designed to look at things almost 7 octaves in wavelength, where the only upper notes are the red orange, and looking at things of colder temperatures or things that have been stretched. So the first stars form, first galaxies form. But more importantly to me as a planetary astronomer is to see things that are not glowing at star wavelengths, but are much colder. Planets, asteroids, comets, be able to detect comets around nearby stars, to be able to analyze atmospheres of planets. So it's an analysis telescope, not a wide survey telescope. First couple of images will be coming out as they do calibration. Once the 3 to 5 month testing cool down finishes, we have a whole bunch of programs that have allocated about 70-80% of the time, and for the first year, with some percentage left over for fine adjustments, as well as events. If they see a comet coming in, or something's going to crash into Neptune or something, and watch this sort of thing, as well as if they discover other Kuiper Belt objects to other planets around the sky. So there'll be a bunch of emerging stuff that'll be there as a typical set.
Can we use the James Webb? This was my last question on it. Can we use that to find somewhere new to live? Because Tonga lets me know that Earth is not like us. It does not want us here, and we should go. It's time to pack it all up. It's time to move.
Yeah, I mean, and that sort of thing is this is going to give us an ability to really try to hone in on planets that might be habitable, as opposed to right now. First of all, with things like Lick Observatory, one of the first to detect a planet on another star, right? To detecting planets, we now have around. We have a number of planets that we've detected, but we don't know much. We don't know much about those actual.
Okay, Landon, how do we get there? Hyperdrive, warp drive, or Stargate?
We don't know quite yet. But I mean, right now we have double confirmation of 4,949 planets.
Oof. Really?
4,949, and we're using the geophysical definition of a planet. That is, defining a planet for what it is rather than where it is.
What is Pluto?
Because the silly International Astronomical Union, a ridiculous organization that does lots of embarrassing things, was dumb enough to have only about 300 people out of the several thousand attendees vote to say that a planet had to orbit our star. So their definition of planet, their definition of planet back in 2006 was so parochial.
That's democracy.
Because you had a couple of people who were loudmouth people who are orbital mechanics people, and they're only interested in orbits around our star. And so to be a planet had to orbit our sun. So those things out there are not planets according to you.
What do they call them?
Pluto not orbit our sun?
As extrasolar round things.
Oh, stop it right now.
Surely Pluto orbits our sun.
Yeah, so I should mention, by the way, since I'm wearing the planet T-shirt that says, first dwarf planet, there, courtesy of Dr. Philip Pinko and his wife.
No, that's what I brought up.
The current designation is Pluto is a dwarf planet. Okay, And just like dwarf stars are
It's
stars.
the Peter Dinklage of planets.
No, come here. So dwarf stars are stars. Dwarf galaxies are galaxies. Dwarf planets are planets. And Pluto has a designation, a dwarf planet. Now, it turns out, from our surveys, that we think the majority of rocky planets are actually dwarf planets, and that Earth is one of the bigger sized rocky planets, and that most of them are Plutoids, that is dwarf planets. So one of the things that the James Webb is going to give us the ability to do is to do some analysis of some of these fainter, smaller planets that seem to be more common. So when someone asks you, is Pluto a planet? Answer right now is yes, it's a dwarf planet, right? It's not a gas giant planet. It's not a protoplanet that's in the process of forming. It's not a Earth scale, large rocky planet. It's a dwarf planet. And so studying of dwarf planets around our star, around nearby stars, is going to be one of the principal things that the planetary sciences part of James Webb is going to give us the ability to see, as well as we're going to be able to look at Pluto and its other companion Charon, which is also a dwarf planet. And Pluto has a weird thing that its elliptic orbit means that when it's close to the sun, it's got a very thin atmosphere, and as it moves away from the sun, that atmosphere snows, freezes out, and so we're going to be able to watch Pluto's atmosphere freeze and turn into a frost on its surface, and understand some rich chemistry that's going on there.
By your definition, then, if it's orbiting the sun or the star independently, it's a planet. But if it's orbiting a planet that's orbiting a star, it's a satellite, i.e. moon.
Well, I'm gonna want to say that it's not simply my planet. It's my definition, right? There is a thing's called a geophysical planet definition. I can give you a link on this thing, where it defines a planet based upon where it is. A planet is a substellar mass body that has never undergone nuclear fusion. So it's not big enough to start fusion in a core, right? And has sufficient mass that its self-gravitation basically pulls it into a spherical shape, defined by an ellipsoid, regardless of where it is. So a geophysical planet defines it based on what it is, not where it is. So, for example,
could a comet be a planet?
They typically don't have the mass necessary to squish themselves in roughly a spherical shape. So, and that answer would be no. But if you have in a planetary system, a close encounter of two planetoids, and one gets thrown into the star, the other gets ejected, right? You have what we call a rogue planet, where the planet is no longer orbiting a star. It's been ejected from the solar system. It's traveling out in free space. The old silly IIU definition it would have said it ceases to become a planet just because it's not orbiting our sun or any star, right? We as a planetary scientist, we're interested in what is a planet, its characteristics. So the geophysical, based on what it is has it ever undergone fusion? Does it have a stellar core? No. Does it have enough gravity that it basically has deformed into a round spherical spheroid shape, right? Regardless of its orbital parameters. And so in our solar system, we have 110 objects that are planets right now. And we're hoping to find lots of those smaller objects around other nearby stars as well. So it's nice to get a body of stuff. But it is there are terrestrial planets and giant planets and ice planets and gas planets, and on a smaller scale are dwarf planets. So Ceres is a dwarf planet. Our moon is a dwarf planet. Pluto, Charon are dwarf planets. But Io, the moon around Jupiter or Europa or Titan and so forth. Those are dwarf planets because again they're not undergone fusion. They have enough mass to warp themselves in a roughly round shape. And regardless of what they orbit or these vague things about clearing and stuff. So the silly IU can just go pound sand because and again this is a definition. I'm not trying to say it's right because it has a majority, but many planetary scientists that are saying, so what are you studying if you're a planetary scientist? What is a planet? Use what a planet is. Many people that study orbits talk about where is it, right? So the orbital people, which is a valid part of astronomy, will be more interested is the object has some orbit where it's dominated and cleared, whatever that vague thing means. People who study what a planet is don't care as much where it is as to what it is. So again, Pluto is a dwarf planet. Dwarf planets are planets. It's a type of planet.
So the moon
Pluto is but here, give me a second. Just give me a second. So basically what you're saying is for us to have a discussion about what something is, we need to set the parameters for what something is before we can have that discussion. We have to agree on the basic parameters to even have a discussion about it. And that goes for everything, even within whatever community you're in. If you're discussing anything, you have to agree on a certain basic parameters on. All right. So what are we discussing? What is a planet? All right. We define a planet as A. All right. So what is a dwarf planet? It's defined as B, and then we can have a discussion on those parameters. But yeah, that's a very good
clarifying.
And we also have this notion of probable planet, right? Because you might have an object detected, but you don't have enough information. But it might be a planet, but you don't have definitive stuff. So we have probable planets as well for those things that are too big. So I have put into the chat, our Skype chat, 2 links to geophysical edition of planet. If you can put those into the chat. But back to your question, I just wanted to.
But didn't they have to like change the definition because somebody came up and was like, well, some dude came up, he's like, cool, I'm naming these 40 planets I just discovered. And they're like, all right, now hold on a second. My very excellent mother, and we can't have an additional 110 letters after that. The poor school children. Will someone think of the children for once?
So let me give you an analogy. You have the periodic table, right? And we now have 118 elements. So do we sort of decertify everything above carbon because it's too many things for a child to memorize?
Yes.
Do we decertify hydrogen in an element because it's too light?
It's too light. We got to get rid of it.
Do we decertify helium because as a chemist, it is very difficult to have helium compounds. So you chuck that out as a chemical element.
I had helium in this cup earlier. It all left. It doesn't deserve to be on the periodic table. It's unreliable.
Landon, as you are of a scientific mind, a friend of mine asked me to ask a question on this show that I normally go on, Mystery Hour. Sure. Is there any logic to the layout of the periodic table? Because it seems to be
balanced electrons.
Yes.
Yeah.
That's what Mikey said.
Balanced electrons.
Yeah. Also, so orbital characteristics, and then with the notion that those orbitals and orbital classes dominate chemical properties, then vertical strips have similar but not identical properties in chemical, and as well as is also talking about shapes and sizes of the outer shells and reactive stuff. So there's similar properties that Mendeleev's original table have been revised as you find.
Because when you look at it, it looks pretty random, especially when you name the elements.
Well, the names are random because they tend to be named after people or historical names and so forth. But if you look at the properties, you see some as you go down line, some similar properties of alkaloids being in this part, metal being this part, noble gases being in this part, transitional stuff. So they're property classes that you can see because the table sort of organizes in a two-dimensional shape, grid, elements in similarity to their atomic number, the number of charges they have in it, as well as the orbital shells. That's more quantum mechanical properties of stuff, which dominates the chemistry. It also has some physical characteristics there. So that's part of the reason why it's still a useful chart to do so.
When new elements are added, is the periodic table amended?
Yes, and so when the most recent element 118 that was discovered and verified. So it's not just a matter of saying, oh, I thought it, but you have to have, typically you want to have someone else confirm and stuff and measure its properties of things in order to say you really found an atom of that type. Then it goes through the process of that being confirmed, and once it passes scrutiny, then this gets to be a naming process, and its symbol gets put into a new spot. So right now, positions 1 through 118 are all full, right? They've all discovered that set, and people are looking for larger and larger elements in the periodic table. They're getting harder to find for a number of reasons relating to atomic physics. But that it'll go there. But in a sense, we don't exclude it because it's too hard for children to memorize.
Yeah. Speaking of physics, if you guys are patrons, you guys will see the amazing, awesome. I've watched it probably twice now, all the way through. Landon did a very awesome talk about nuclear bombs and nuclear reactors and all that stuff. And it was one. I think that was our first or second thing that we put out on Patreon. So if you guys are not patrons, by all means, hop on, and I think even at the $1 level, you can watch that talk.
Yeah, that was a talk on thermonuclear devices and talking about the things that aren't reactors, but the things that have rapid exponential things of based upon non-classified public sources of what those things are and their characteristics. And
do you think, Mikey, that if we put Landon and Professor Howe in the same room, it'd be like crossing the streams? And
we'd create a singularity.
We would either ascend to sort of like eternal beings or be blown up.
You'd get we would get galaxy brain.
So I am with the James Webb Telescope. What I'm excited about is the puzzles, the questions that are going to rise from the telescope. Science is about questions. Science values questions over supposed answers, right? A great scientist is someone who can ask the right question to the right people, the right time. That's why they're great. And so they pose these questions. And so it's more than simply Webb giving us pretty spectrums and narrow few pictures of things. It is the things we don't expect where you say, why is that? What is that? That is really weird. Is that a one of a kind, or is there something we've not seen before? What's going on here? It's those things that are going to probably be the most exciting stuff, rather than say, well, there's a comet and it has carbon dioxide. Yeah, we know that. It has water. Yeah, we know that. But what is this, right? The formations, all the models we have of how the first stars form, the first galaxies form, we're going to probably find things that say, we didn't expect that. What is that? Why is that? Those are the things I'm excited about. And in planetary science, what kind of chemistry is going on in some of these planets that aren't frozen cryogenic ice balls and aren't boiling magma producing things, but in the middle where the temperatures are right, that the chemicals can dance and form interesting stuff, right? Particularly if we find some self-replicating chemical system, whatever it is. On Earth, it's carbon-based things, but whatever it is, that has complex, evolving chemicals. It's the questions that Webb will pose that I think are going to be quite significant, and that's what I'm excited about to see. We didn't expect that sort of thing. I mean, just like the accelerating universe. When I was going to college, the debate was the universe open or closed. Well, the answer today that we have is it appears to be accelerating, worse than open. It's opening up wider and wider and wider, and the answer is, well, why? Right? What is this dark energy? What's this nature of the stuff? But then there's also this dark matter, which is not dark energy, which influences gravitational fields, but we can't see it. And what is that, right? So the James Webb Telescope won't be able to see, we presume, dark matter, because its dark matter appears to not react with light, electromagnetic radiation. Right. It has gravitational influence, and so we might be able to see motions or shifting of something in the process of galaxy forming, will tell us about the mass distribution and the gravitational field distribution, which will tell us something about are early galaxies dominated by dark matter, and that you had a lump of dark matter that normal matter, gravitation got bound to, or did the dark matter find the normal matter, or what the thing is? We'll find these puzzles going on, and it's the questions that James Webb will produce that will turn it into a great telescope. Besides pretty pictures.
See what?
Yeah, like 800 months.
What I like. Calm down, Mikey. It's not your birthday.
So it'll be my birthday by the time we get some damn pictures.
And you'll be 96. But what?
Yeah, he'll be your age, Wade.
Shut up, you prick. What I love about actual proper scientists like yourself is the three most important words for you and guys like you and people like you is I don't know.
Yes.
That is why everything is a theory. The theory of gravity, because someone could come along and disprove it. You leave it open-ended. The theory of evolution, you leave it open-ended because someone could come and disprove it. So all these things, when you get these charlatans that sit there with these certainties and they're sitting there going, "This is fact," and then someone comes along and disproves them, and they then have a go at the person disproving them because it goes against their narrative. It goes to show that they're a fake actor. They're
well
a fake
said.
actor.
Well said, because science is about questions. Dogma gives you the answers. Right? Dogma says, "Here's the answer." But why? Because I said so. Right? Science says, well, "What about this?" Right? About so now in science, what we call a theory is a thing that has an astounding amount of experimental evidence to show that it's plausible. However, it's also still falsifiable. So the reason why string theory is not really a proper theory is because it is yet to have a test that we can do to say thumbs up, thumbs down, right? So I call it a hypothesis at this point. But understand, when a scientist talks about a theory, it's something that has been elevated to the highest level of confidence, where test over test over test keeps coming up. And so relativity, quantum mechanics, evolution, these are things that have survived hundreds of tests and have a high confidence level, but it's not dogma.
But you don't have that. You don't have the arrogance of certainty.
Yeah.
You don't have the arrogance of certainty. You leave the door on the latch for someone to walk through and go, "Here you go, some more evidence."
And if it wasn't falsifiable, if it wasn't then it wouldn't be a theory. It wouldn't be scientific, right? For the set. So and thing, when I talk about, when someone says, well, how old is the Earth? I'll start off by saying, if our model for how the Earth forms is reasonably correct, then data suggests blah, right? The reason why I don't say number is, first of all, it's not an exact number, but also the fact that I want to say what the question is and what are our current approaches to that. And again, in science, if you get an answer, and it fits the current known thing, that's nice. You just buck in the bin of more confidence. But if you get an answer that is unexpected, then people get right excited, right? When we discovered that the space was accelerating, we didn't expect that. And we got quite excited, right? Scientists get really excited when they realize they don't know something.
Yeah.
Because now
Something
a flood
to
of
do.
questions comes out. There's a flood of questions come out and so forth. So James Webb Telescope, its greatest achievements will be all these questions that come up when you think you understand how a star forms. You think you understand how a planet forms. You think you understand how the range of planets are there. James Webb is going to, hopefully, if it does its job, produce questions that'll puzzle us even more to say, "Oh, we didn't expect that," right?
And that's why you can't get through to theologians, because we're doing all this stuff to disprove them every day.
And the dogma says this is what it is. Science says this is a question. And in fact, we value the question over the answer. If you get an answer, that's just a merely stepping stone to have more questions.
So basically, you're standing by the whole the more you know, the more you realize you don't know.
Exactly. And falsifiability, right? So you have to talk about how something can be disproved. And so my tests on general relativity it would have been great if I found something where the experimental evidence disagreed with theory of relativity, because then theory of relativity had to be modified or chucked out, right? Relativity is not dogma, it's a question.
Never to speak to my oldest daughter, because when I say, because I said so, she comes back at questions. I'm fucked.
I'm gonna send her a link to this, and I'm like, hey, when Dad starts kicking off, just play this, okay? Just play this clip.
So it really is about the, so that's why James Webb Telescope was designed to understand better questions involving star formation, galaxy formation, planet formation, early planets, early stars, early galaxies, and current planets, comets, those sorts of things, to be able to ask the right questions. So it's an analysis telescope, not a widespread panoramic thing, a very narrow analysis telescope. So when you know something is there, you can point James Webb at it and reanalyze it to a capability we can't do on Earth because of glowy Earth, atmosphere, all that sort of stuff. Yeah, interference with stuff. So it is designed to minimize interference with itself, designed to be able to operate. We given the amount of fuel that's on board, we believe we have at least 10 years worth of time on it. And Mikey, we can come back maybe a year from now to talk about, well, what has James Webb done, right?
No, I'll be out there with I got a helicopter. I'm flying out to the satellite to kick things off because they're taking too long.
Mikey's sitting there with teddy bear. Why won't I give me the pictures?
You kind of, your helicopter will run out a couple of kilometers away from Earth's surface, and you've got, a million kilometers to go, kilometers. So
by the time I get there and back, maybe the pictures will be out by then.
Yeah.
Assemble the drone.
You'll get a couple of pictures as they're calibrating right now. They got to focus it and cool it down, but you'll get a couple of pictures that'll come out during that 3 to 5 months testing period. Believe me, a lot of astronomers are very impatient as well to be able to get their programs started. And but again, maybe a year from now we can have a show talk about, well, what are the questions that James Webb has opened up, and what are the answers that are expected versus answers that are unexpected? And probably the cool stuff will be, we didn't expect that sort of thing. So
I can't wait for these pictures to come out. It'll just be Mikey on his chaise lounge having a cigarette.
And understand, also the spectras, right? The frequency distributions that it's going to have are not going to be, photogenic, but they'll tell us a lot about the characteristics of what it was that observed. And then people ask, well, what is that?
We'll definitely need help with that, and figuring out what those are and interpreting them for the for the masses. But I think that would be a really nice thing when those do come out. If we can have you and us, we can try to figure it out. We can make it a kind of a puzzle.
Yeah, Landon, will you be our key?
Yes. Yes.
And so right now, for what's happening right now with the telescope is, besides the cooling down, its other next function is to fine tune those mirrors, those special beryllium mirrors that are gold coated. They have these little actuators that can move the mirror 1/10,000,000th of a millimeter, 10 nanometers. I mean, that's a.
What's that in inches?
Do not pacify him.
Yeah.
Really small.
Okay, I'll get that.
Sub wavelength, because again, the wavelength of light goes from the visible light goes from about 350 nanometers to about 700 nanometers. This is tuning it to within a fraction of the wavelength of visible light, right? Really, really small sets. So they're going to really dial in the focus. And that's important, because if you want to see, be able to distinguish the atmosphere of the edge of a planet to the middle of the planet, you need that focus really sharp. And so they're going to be homing in on the fine adjustment sharp stuff, as well as testing how far is the field. Typically, if you have a telescope, when it sees first light, you say, okay, here's a star. It's roughly focusing. But at that point, you start to make sure the mirror is parallel, things are aligned, and then you start looking at, is the field flat? As you have it, look at a general area that is fairly uniform in brightness, and you see, is the corner of this a little bit brighter than this corner, right? Is this cells a little bit sort of sense with that, so you can calibrate the instrument. And that's part of the science mission, because the scientists, you just don't know, the scientists, they have these things that are just going to be a bunch of noise and irregular things, so forth. It won't be useful to give the scientists data. And so this mission checkout thing, they'll try to be as short as possible. It could be maybe as short as 3 months, because we know that's going to be at least the time it's going to take for it to cool down. And it could be long as 5 months if they have to do fine tuning of stuff.
There'll
be a couple images coming out, a couple spectrum coming out, reports on how sensitive it is, those sorts of things, bad pixels, that sort of stuff.
I have a prediction. The first picture you'll see from the James Webb telescope is basically Mikey looking like your grandma doing her first FaceTime, holding a jerry can and a wrench, going like,
yeah. But
in his homemade spacesuit.
At least we know they didn't leave
some
the
garbage bags.
At least
Mikey wrapped in tinfoil with a jerry can.
We know the lens cap is not been left on, right? It'll have stuff there, but again, it's tuning and calibrating and giving that fine micro adjustments of the mirrors and understanding the characteristic and capabilities of stuff. During the first year's service, there also will be a deep field stuff. There'll be some of the, because again, there are a bunch of programs that have come about, and of the 266 proposals that have been accepted for using the telescope, 13 programs are ones that have longer time, where there's going to be one of the things it's going to do is going to stare at a spot for a long time to get the kind of the equivalent of the deep field of Hubble. Except Hubble has fairly wide spectrum. This is going to be narrowing in, and so there was a discussion about, well, what things should you stare at, and so people introduced proposals. And one of the things for the case of galaxies are some of those in the Hubble deep field that has some of those really tiny faint red blobs that they say, here's a galaxy that's 12 billion light years away, right? And it's just this tiny fuzz thing. Well, not only does the telescope have a much wider mirror, so it can do much fainter, but also has much finer resolution. So instead of having a fuzz galaxy, we'll be able to see some structure of it, and we'll be able to see potentially fainter galaxies around it and back of it that the Hubble was unable to see, as well as a wider spectrum. So as well as, for example, I know I have a colleague that is going to be looking at Neptune, because Neptune's a really weird planet in terms of it's warmer than what we think it should be. Its temperature on the surface is hotter than what you would expect if it merely is being heated by the sun. It has receives light from the sun, a little faint, but it has a higher temperature, and we're not quite sure why.
I'll go check it out. I'll be right back.
So it's going to give us some notions of stuff, but be able to look at something like on Jupiter, the Great Red Spot. This storm that Galileo saw back in the 1600s has been going since that. That's a couple of Earth's diameters and size. It appears to be winding down, maybe sort of kind of as its color has changed from the days when it was really red to now it's kind of a less obvious red spot. But Webb will be able to point at that spot and look at do a chemical analysis of the upper cloud tops of the red spot and give us some notion of what the heck is this storm on Jupiter has been going on for centuries, and is it winding down or is it ebb and flow, and what are some of the better chemicals, even better than, for example, the space probes around it that were able to give us nice pictures, because again, even like the Juno spacecraft, amazing spacecraft currently orbiting Jupiter that dives in deep, the spacecraft is not able to look at these area spectrums and give us some notion of the chemistry of the cloud tops to understand with how Jupiter's thing. But looking at Titan, the big sort of methane, large dwarf planet that orbits Saturn, it's got some really interesting chemistry in its atmosphere. It's seen as sort of a early proto-Earth that's been frozen in time. And looking at Europa, this ice ball dwarf planet orbiting Jupiter that appears to have an ocean whose volume is around 4 to 7 times the volume of Earth's oceans, right? It's got this vast ocean with this ice sheet on it, and cracks where the sort of the icebergs crack and stuff comes up. You got this sort of interesting sort of colored goop that's there. We're going to be able to look at the atmosphere of Europa. It's a very thin atmosphere as it's outgassing and other stuff to try to get a better notion of what kind of chemical soup might be underneath the surface of Europa. So that we want to send probes there, but it'd be a good idea to have some questions that the probes are trying to study, as opposed to just going there and hope you can find something. So all these questions it's going to be generating is going to be really fantastic to see.
Landon, this has been absolutely insightful, and I don't know about the rest of the guys, but I've learned so much about this space telescope that we thought was like just a gimmick. This is shit up, real deal kind of.
Thank you. So let's think about a year from now or so.
No, we have to do it on Mikey's birthday. We have to do it on Mikey's birthday, and behind you need to have all the images that this telescope has taken, and you need to go through one by one.
And what
with
day
a laser
is Mikey's
pointer.
birthday?
My birthday is August 5th.
August 5th.
Yeah,
and
I think it's a Thursday.
so we'll have some.
If that's a Thursday, that would be great.
It's either a Thursday or a Wednesday.
Mikey's birthday show. That'd be.
But August 5th is.
Oh, it's a Friday.
August is a Friday.
Oh, but Mikey's birthday eve. Joe.
There you go. Like that.
But week.
Now, obviously.
Landon, this has been such an insightful episode, and I can't speak for everyone else, but I have learned a lot. No, thank you.
And thank you very much for having me on. I'll point out, say we do the August 5th. That'll just be 1 month into the science program, or 2 months of science program. So we won't have much in the way. We'll know about what the telescope's capable of doing, and we'll be able to talk from its first sets of stuff. So if we talk about August 5th, in 2023, we'll have then a full year of stuff. So we usually do both things. Is telescope working? How good is it? What are some of the first images to kind of give you some analysis of exciting stuff, some of its first data coming out. Now, understand that we might not have science papers because the way that James Webb is working is a number of the scientists, if it's your proposal, you get the first, even though the data is available to everyone, you have the first right to publish on it, right? So you don't poach on someone else's program, but then after a period of time, anyone can use the data for that. So it's not that the data is secret, but that the people who put the effort to get a program accepted are the ones that have the first right to publish. And so it may be by the time of Mike's birthday, we'll have had the first science programs, but we may not have the published papers yet. But we should talk about that. And a year from then we'll have some of the things where, so yeah, August 5th will be about the telescope and how well is it working and what are some of the first images that it's produced. To the year from now is, well, what questions do we have that we didn't know to even ask? So thank you again. And please,
Landon, where
please
can
continue
anyone
to enjoy
find
our favorite universe.
Landon, where can anyone find your work and get hold of you if you want to plug yourself?
Well, okay, so I have a channel that a channel that I'm developing with my producer Dave McInnes, called Our Favorite Universe. Right now, you'll just see 2 videos about making espresso. Right. My producer first of all had COVID, and he had another appendicitis and so forth, and then I've been involved with the sea contest. So stay tuned. That program will come there. I have a very old school website.
Is it on Cinefilm?
It's our favorite universe, right?
Yes.
Okay.
So, and then my web page is, did I get the right thing? Copy. Let me make sure I got the right link there. The web page should be in a link there. So that's a web page for just, that's a whoops, I typoed that. Let me do that. Let me correct that. Let me correct that thing. So it is here. That's even old HTTP thing. So that's just my general page that's about me. But look forward to Our Favorite Universe, because I'll be the primary focus will be news from Our Favorite Universe. I'll take
and Mikey's birthday newsletter.
Absolutely, because what I'm going to do is I'm going to say, here's a news event that's scientific, and here's why it is interesting. Right, there'll be a couple of minutes. But those are in the can. Those are producing right now. I'm focusing on the International Obfuscated Sea Code Contest. Fantastic. And you might say, what in the heck is that? That's this thing here. This is the other. I am the co-founder of the oldest contest on the internet. It's a C programmers contest. It started back in 1984, and we're retooling it. So I'm working on.
I was 3 years old.
Yeah, and so it is a collection of C programs, really style C programs that are extraordinary. They're small, compact, but people do things like write programs to do chess, flight simulator in only like a couple thousand characters of source code, right? It's amazing collections of things. So on the Lambda calculus stuff that's done. So look at some of the winners there. Extraordinary what they do, and so we're retooling that. So right now I'm focusing on retooling that contest to have a 28th contest come up. I'm working with Dave McInnes, who's now out of the hospital for the second time, and we're getting that program going forward. And that's about it. Thanks again for this wonderful contest.
Thank you, Landon. And this has been episode 1, series 2, season 2, as they say in the States, of the BIM podcast. So
Yay.
Thank you, Landon. And for Mikey, for Brenna, for Jartan, thank you for actually coming.
Oh.
For Ozzy.
Oh.
Ozzy, he's so cute.
This has been the Bin Podcast. Welcome to season 2, and yeah, thank you very much for enjoying this and watching.
And I hope you continue to enjoy my favorite universe. There's a link I put in the description about where is Webb and what it's doing right now. You can put that on the link as well if you want to see.
It's all there, mate. It's all there.
What's there. So thanks again.
Bye.
Cheerio.